We are recording the proceedings, and so far what we've been most recently doing is looking at how we can use chemistry and charge separation and the desire of different elements to draw electrons to them or pull electrons loose from other materials spontaneously or naturally. We can connect the two elements that wish to exchange electrons, which we will call terminals. So we take pieces of metal of various types, and these metals have competing desires to gain or lose electrons. So we connect these different metals via some kind of conduit, some kind of conductor between them. And now the electrons that are being transferred between them flow. Now we can harvest this flow of electrons as electrical current, and we can do all the wizardry of electronics that we have developed over literally the past essentially 200 years, using the tricks of this chemical means of supplying charge from one entity to another. So we looked at this idea of how charge is transferred. We made some definitions of different quantities that are involved. These terminals ended up being one where the electrons are being lost, and we called the one where electrons are being lost the position of oxidation, from the tradition of many elements losing electrons to oxygen. We called the other one, the other terminal, where electrons were being gained. We called that reduction, and we claimed that these terminals were named the anode and the cathode in a storage battery or a chemical battery, the typical battery that we buy at Walmart, that we stick in all our devices like flashlights and other things that require such electrical power. Now, another thing we looked at was the fact that these chemical spontaneous running batteries are going to be losing oomph over time, essentially because they're losing their fuel. One electrode is actually losing metal, and as it transfers electrons, it will be getting lighter and lighter and lighter the whole time. At the other end of the reaction, in the liquid part of the reaction, the ions are coming out of solution as the electrons are transferred. So it is also losing its concentration and ability to be able to supply and sustain that electrical current. So eventually, as we all are well aware, batteries die because they no longer have the fuel in these chemical terminals to supply the flow of electrons. But we have overcome that over the past 100 years by developing rechargeable batteries, which we have to restock the terminals. And very simply, the way in which we restock the terminals is run the chemistry in reverse. Now, this doesn't come for free. You must supply energy to do so. And of course, what that means we do is we plug it into the wall. When we plug our recharging batteries into the wall, essentially the battery is literally running backwards, and it's replenishing the juice ions that were being lost in the spontaneous flow. It is building up the metal on the terminal, which was losing metal in the spontaneous flow. So after we recharge the battery, we can take it off of there, leave it back in our device, and now it runs in its natural form that it wants to run. The element that wants to give up electrons gives up electrons to the element that prefers to gain the electrons, and this spontaneous process can continue until the terminals again are diminished in their fuel supply and can't do it any longer. And as I pointed out to you, we should really stop and appreciate the technology that has been developed certainly in the past 40 years, I would say. The rechargeable battery industry has really stepped up and really gotten good. And as I said when we met on Monday, all you need to think about is just how many times you have charged your phone. It's pretty remarkable how stable and how, what a chemist would call reversible, we have designed this process. And the rechargeable batteries, of course, as we all know, they have a limited lifetime. I mean, most of us usually upgrade our phones before the battery needs to be replaced, but that's not true for everyone. People like me, I don't really care to upgrade to a better 4 more cameras or any of this other stuff. It doesn't really interest me. So I have had to replace my rechargeable battery in my phone once, but only once over the, I don't know, 6 years I've had this same phone, maybe 7 years I've had the same phone. I don't, something in there. Okay, so that's all fine and dandy and interesting, but it turns out that this process for the chemical battery has limitations. It has various types of limitations, and I can just enumerate them to you very quickly. First of all, there's only a limited amount of output voltage that we can generate from the individual cells. Now, what we do to overcome that, as I talked about, is you start sticking them together to work collectively. You stick the anode of one to the cathode of the other, the anode of the next to the cathode of the next, meaning you put the tail end of a battery touching the tip end of another, tail to tip, and you're connecting the batteries, as we call, in series. And literally, when you connect them in series, you're multiplying the voltage of each output cell by the total number of batteries connected in the connection. So the standard for most batteries is 1.5 volts. If your device takes 4 batteries, it's running on 6 volts. Because each battery connected together they're pushing together, if you like. They're pushing their charge collectively when you do something like that. But what I will point out to you is ultimately there's a limit to how many of these batteries you can put in series. As you can imagine, in a car, now that we are beginning our foray into electric cars, which run on storage batteries, rechargeable batteries, of course, there's probably, I'm not sure because I'm not an engineer of this type or that works closely in this field, but I'm willing to bet there's 1,000 pounds of batteries in that car. So there's going to be limits to how much of this we can do. And those batteries are all hooked in series, and they're hooked in series so that we can get enough oomph out of this car so it can drive us at 50 miles an hour for a couple hours before it needs to be recharged. Okay, so ultimately, what we run up against are limits in the effectiveness of each individual cell and how many cells we'd have to put collectively together in order to build up a huge current or a high voltage case. And of course, the other probably worse issue is the fact that they run down. It's a pain in the butt to have to constantly recharge your batteries. So ultimately what this means is that the chemical storage battery and its action of generating electricity has been replaced and or modified with an alternative form for general usage by the public. And I'm sure we're all quite aware of it. Now, the main differentiating definition for what we call the chemical battery in terms of its current is that it is a direct current. And I'm sure we've all heard the term DC electricity. That is because electrons flow from the anode to the cathode, period. From the anode to the cathode. And flowing from the anode to the cathode means the current flows in one direction only. So that is a direct current. Current moving in one direction only. In a battery, current moves from the anode to the cathode. Now, so the devices that are being powered by that are designed, of course, under the capability of handling current flowing in one direction only. But as I pointed out, there's an alternative approach that we can use to generate current, and we have already talked about it. And that is by this phenomenon that was pioneered by Faraday, which we called magnetic induction. Remember the weirdness of when you change a magnetic field that you expose a conductor to, causes the conductor to generate its own magnetic field to replace what you have taken away. And how does it generate its own magnetic field? By moving charge. So when you vary the magnetic field in a conductor, it makes a current in the conductor, and the ultimate goal of this current in the conductor is to replace whatever change you have made to the magnetic field that the conductor is being exposed to. So the wizardry of the engineers of the 1800s, including Tesla and Edison, actually mainly Tesla pioneered it and then Edison borrowed it and ran with it, is to generate electricity, not chemically, but generate electricity by magnetic induction. So what I'm going to finally do is go to my slides, and what you will notice, those astute members of you will notice, is that really I'm jumping way forward in my slides. I'm skipping, where we had ended up was a discussion of corrosion and rusting, and we did a little bit of discussion about how all that occurs as electrons are transferred between objects. There are maybe 10 or 15 more slides past that I'm just going to blow off, and I'm not going, I promise, to ask anything at all with anything to do with any of those. The main reason being is recognizing the pace of what I've been covering, and then where I really, some other topics that I think might interest you and also be important that we cover in this class. I'm just going to skip some of those things, but I certainly want to point out this slide that says what I want to say regarding this generation of power, and we'll have a little discussion about it. So I'm going to do my presentation and come to my slides, and you'll see what I mean by my skipping ahead here. I've done a big jump in my slides. Let's see, to here. Now, I'm not sure, does it say what number this is? I have jumped all the way to slide 49 in this lecture 5 collection. So again, there are probably maybe 10 or 12 slides that I have passed over, and they discuss current and they discuss resistors and how to make a circuit and things like that with a direct current circuit. That's really okay, I guess, but as I said, there are so many other things that I would really prefer to talk about with you that I'm going to jump ahead to this particular slide where I'm showing right now. And the idea here is this is a cartoon representing what the power company does. But there's much detail for this slide for me to fill in on this slide. And I think I've already mentioned some of these details, but let's say them again. The electrical power company does not make direct current. The electrical power company makes what we call alternating or AC current. And there's a simple reason for why it does this. It generates electricity mechanically and not chemically. Now, when I say mechanically, what do I mean? It generates electricity by moving parts of a device instead of generating electricity by a chemical reaction. What you have essentially are conducting loops. Now, that's what this thing is trying to represent. It's not a loop so much as a square or rectangle, but I have a rectangle of conductor. And believe me, the power company does not move one loop of conductor. It simultaneously moves thousands of conductors at the same time in order to generate the kind of current and the high voltage that is demanded in our current society. We're power hungry, and this turns out to be an excellent source of power by doing this mechanical generation. Okay, so what ultimately you need is a magnetic field. So at the power company, there are very powerful permanent magnets that have been made from something out of the ground or in some way enhanced by scientists so that they can make a permanent magnet. And between the poles of this permanent magnet is a very intense magnetic field. So there is a magnetic field which now they rotate the conducting loops. And as the conducting loops go to wide, down to thin, back to wide, down to thin, the magnetic field passing through the loop varies constantly. As the magnetic field, as the loop swings this way, there's less magnetic field going through it as it gets flat. So the magnetic field is lowering as you flatten the loop. And so it says, I don't like that. I need to replace the magnetic field due to my flattening of my loop and making it long and thin. So it generates a direction of flow of charge to replace the magnetic field that it lost. But now as it turns from flat back to facing sideways, now it's getting much more magnetic field through all the components of the loop. And it says, wait a minute, now I'm getting bombed with too much magnetic field. I need to fight against that and stop it. So I need to put charge in motion to oppose the magnetic field. And when I put that charge in motion, it's literally in the opposite direction. So half the time, the current flows in the conducting loop one way. The other half of the time, the current flows through the conducting loop the opposite way. Now, as you can imagine, as it's doing this, it's also passing through no current. So it's going through current to the right. The current to the right gets to the max. Then the current to the right starts to fall down and actually falls to zero. Then goes change the current to the left. And it goes current to the right, current to the left, current to the right, current to the left. So it's just constantly oscillating. And if they move the loop exactly, as we will call periodically, meaning there's an exact frequency of turn of the loop, then the current has an exact frequency of oscillation between plus or one direction and the other. So the current's going this way, then that way, then this way, then that way, then this way, then that way, very periodically. It doesn't vary like every some seconds it's going more this way, then it goes slower this way, then more this way. It's nice and smooth in its oscillation because, and only because, the loop is turned at a constant rate. So that alternates the current in a nice, as we call it, sinusoidal pattern of up and down and up and down. Okay, so then as the current alters up and down and up and down, they can harvest this and send it out. So anytime you plug into the wall, the current that is being fed into your device out of the wall is this mechanically generated alternating current, which periodically shifts direction. Now, the industry has decided here in this country that this alternation be 60 cycle. Now, what does it mean to be 60 cycle? Every second, the current is flipping over 60 times. So that's pretty quick when you stop to think about it. Every second, the current has 60 complete oscillations from this way to that way, to this way to that way, to this way to that way. So again, that is industry standard. Also, the output voltage that is put into our alternating current plugs is an industry standard. It's somewhere, it's a peak of 120 volts, but it's somewhere typically between 120 and 110 volts that come out of your plug. Now, of course, that's your standard household plug. We have devices which require more voltage than that, like a dryer or a stove or something of that type. How can you tell those devices? Well, certainly, first of all, the wire that is connecting them into the wall is much heftier than the wire that connects, say, a lamp into the wall. Look at the plug on the lamp and the wire connecting the lamp to the plug. You will notice nice and flexible. You can hide it under stuff real easily. Then compare that to the plug on your air conditioner or the plug on your stove, and you'll note that the cable has got some real girth to it, because literally the conductor to pull all that current that the dryer or the stove needs has to be a big tube. So there has to be a lot of metal in the conductor so that it can support the flow of all that electricity through it to power the clothes dryer or to power the stove. The wire on the lamp is much thinner because the draw of current or the pull of electron flow required to power the light bulb in the lamp is much, much less. Now, what would happen if you tried to put the skinny little wire onto the stove or the clothes dryer compared to the big honking thick wire that it needs? Well, the current will still try to flow through there, but there will be so much friction by the electrons trying to zoom through there, they will generate so much heat that you will quickly overload that wire, and it'll cause an electrical fire. You'll heat the wire up so dramatically by trying to pull so much current through it to feed the device's electricity hunger that you will cause a fire to happen as a result of that. So we now should recognize that when we are using household power, we're doing it mechanically for a couple reasons. The main reason being, this can just, as long as the power company is spinning the loops, the power stays on. So of course then comes the issue, how does the power company spin the loops? Well, it has like a little motor to spin the loops. The motor has to be powered. How can the motor be powered? Well, some power companies do it by burning coal. Then they put it into a little steam engine and it moves the loops around. Some do it by burning natural gas. All of them do it by consuming one form of energy and converting it into electrical energy. A lot of places use nuclear power. They split apart the atom's nucleus, releasing energy to build steam up and then make a steam turbine spin the loops. So you can do it in that fashion. Interestingly, what Edison did originally, you might not know this, but it's really a cool story. He wanted to power New York City, and the main source of energy he decided he would use was gravity. As of course you drop an object off the end of a building, we know that it quickly begins to move very rapidly. And what Edison wanted to do to power and make the loops move was use the trick of gravity. So what did he turn to? He turned to Niagara Falls. If you go to Niagara Falls, there's a big altitude difference between Lake Erie and Lake Huron, I believe. I believe that's where the Niagara Falls are. And when the water flows from one into the other, it falls very dramatically in the gravitational field of the Earth. And what Edison did was just put some paddle wheels at the bottom of the falls, and they were just constantly spun by the falling water over Niagara Falls. He connected them to loops. The loops made current, and he piped that current all the way from Niagara Falls, which is pretty far away, I'd say maybe 200 miles away, to New York City, to power New York City. They still, to this day, have the original Con Ed, that's what they call it, Consolidated Edison became the company that they made electrical power from Niagara Falls with. They still make electricity at Niagara Falls, and I do believe the company is still called Con Ed, Consolidated Edison, that makes the electricity at Niagara Falls. Okay, so the bottom line is somehow energy has to be expended in order to make electrical energy. You don't get anything for free. So to spin the loop requires energy. And again, you can do it with chemical bonds breaking in fuels such as natural gas or even oil or coal, or as I said, Edison he did it with gravity. You can do it, of course, with wind power. That has now become a major source of doing this. There are now windmill farms located in regions where there are high funneling of air pressure changes that make the air move very rapidly, so you can easily spin the blades of a turbine and then turn loops like this and generate pretty sizable amounts of electricity. So that's now also a very common way in which we generate electricity using the power of wind, of course. Okay, now there comes other issues though. And the main problem with alternating current is literally the alternating current. Let's think about, let's return to the idea of a simple electric motor. A simple electric motor almost does this process in reverse. As current flows through a wire, it can interact with a magnet attached to a device. And so as the current flows, you can make the magnet begin to move. But what you would probably begin to think is that this is going to be facilitated for direct current, and it is. Many devices operate on direct current, whether they're plugged into alternating current or not. For instance, think of a fan. If you attach a fan to alternating current, what I think you could envision is there would be a period of time where the blades spin one way and a period of time where the blades spin the other way. So there should be alternating direction of the spinning of the blades because of the alternating current due to the little magnetic motor that a fan uses, for instance, to convert the electrical energy into the mechanical energy. Well, of course, we know that fan blades only spin one direction. So what many devices like fans do is they take the alternating current and somehow mess around with it, smooth it out, and make it direct current before they put it into the electrical motor. That's the most common trick. You make the alternating current into direct current, and then we know how to put it into a motor to make the motor work one way and one way only. Now see, light bulbs don't care. You can flow current through a light bulb left, you can flow current through a light bulb to the right. It doesn't care, it will still light. And one of the reasons we keep it at 60 cycles is so that our eyes cannot discern the flip in current, and we don't see the light bulb blinking as the current flows left to right, left to right, left to right through the light bulb. The alternating current is set at such a high frequency that we never see the current going through zero because our eyes just aren't quick enough to pick that out. But literally in your light bulb, when you plug a light bulb into an alternating current, they don't have any rectifiers that make it DC. They just flow alternating current through the light bulb, and the light bulb lights whether the current is moving to the left or the right. It doesn't seem to care. Okay, so what I'm going to say then is this is going to be the conclusion of my discussion of the use of charge in motion, in particular to generate really important things like electricity. So our discussion of charge in motion for now is over. So what I want you to take from that is that if you look on these slides, there are still a number of slides remaining in this collection of slides. Let me be specific. Beyond this slide here, there are some 14 more slides left. My point is this: we could talk about them and discuss what's going on in them and things of that sort, but I have other things of interest to us that I think, and also of interest to what the other people in the department think that should be covered during the course of this class. So we're just going to skip all that. I'm not going to ask anything at all to do with anything other than the things I have discussed personally, the slides I have discussed personally. There will be some Moodle references to the things I've discussed, nothing else. So what I want to then do is to get rid of these slides and move to our next set of slides. Now, it turns out that these also have something to do with charge in motion or charge, but this is now a discussion of how charge is used to connect atom A to atom B. So where we're moving to is we're moving away from individual atoms and we're moving into collections of atoms. And what this is going to later let us discuss is the very important industry of plastics and polymers, and even the very important idea of how we ourselves are constructed from collections of atoms. So that's ultimately what we want to do here, talk about how atoms combine with one another to make compounds and molecules. So what I have most recently posted is another lecture, and this lecture is lecture 6, and that's where I'm going to start. Lecture 5 is done, and as I also mentioned, I probably left off maybe 15, oh man, maybe more like 20 slides from lecture 5, and I don't really have any qualms about doing that. And now we're going to move into lecture 6, which focuses on combinations of atoms. And it shouldn't be surprising, based on all the discussion we've been having about charge, is that charge plays a large, important role in atoms in combination as well as it does for individual atoms. Now, the question as to why atoms are motivated to combine, I don't think we're going to attempt to answer in this class. If you want the information that deals with just why, and that's a very important question. As a matter of fact, that's one of the things that motivated me to become a scientist in the first place. Probably the number one question that did that for me was why. Just why in the world do the elements of the periodic table combine with each other anyway? What's their motivation? Why don't they just remain pure elemental form? I mean, there's plenty of elements, and so we would have plenty of materials that we could work with, but I'm sure we're all very familiar with the fact that most materials that we work with, I would say the vast majority of materials we work with are not pure elemental forms. The vast majority of materials we work with are combinations of the elemental forms. Regular, repeating patterns of not random combinations, regular repeating patterns of combination of the base elements. So again, last time I will say it, we are not here to delve into the motivation for the combination. Of course, we do have understanding of that, but we are here just to review the types of connections and the ramifications of the connections that happen when atoms do this combination with one another. So I have this new set of slides, and we're going to boil it down to two ways in which atoms are going to combine with one another. And the first is very reminiscent of this idea, the importance of charge holding matter together. And even the name of them kinds of implies how charge holding them together is front and center in this process. What we're first going to talk about here, as the title of the slide says, is an ionic compound. And an ionic compound is formed when the atoms that are combined. Now, first of all, when I say compound, that should immediately tell you I no longer have a pure element. I'm now going to combine elements. And when I combine elements, if I'm going to have them combine in this ionic compound form, it only occurs when the elements that are combining have a large difference in desire to gain, and I should also include, or lose electrons. So there's a distinct difference in whether you're the giver or the taker. Now, we already have seen the importance and the ramification of that in making a battery. When I put the zinc near the copper, spontaneously, electrons run away from zinc. Spontaneously, electrons were sucked up by the copper ions. So that's one instance of this. Now we're saying if I have large collections of atoms, I can now have massive transfer of electrons from one to another simultaneously, and I will form these entities, which I will call ionic compounds. Okay, so ionic compounds are formed when the combining elements, turns out, are far apart in the periodic table. If you're going to relate it to what goes on in the table, that's what we would say. And elements, it turns out, from the left become cations. They're the givers. Elements from the right gain electrons. They become anions. They're the takers. So it's kind of much the same as what we've seen in the battery idea. But now what happens is, instead of happening on a huge strip of metal that we call a terminal, transferring to a huge strip of metal, which we call a terminal, now this is happening on an individual atom basis. One atom of the giver and one atom of the taker simultaneously do this process individually. Okay, now, ionic compounds are typically formed between metals and nonmetals. The metals are the givers, the nonmetals are the takers. So this slide I have shown you before when we were talking about which elements were good conductors of electricity. And what I mentioned to you the last time I showed this slide was that the elements in blue and purple are metals. You'll notice they are gathered, as a matter of fact, they represent about 2/3 of the table. And they are gathered on the left side of the table. These are what, again, I will call the metals. And what we talked about before was that these were great conductors of electricity. They really supported the flow of charge in them. So they could be used to make conducting wires and things of that sort. Now, the things in the upper right-hand corner in green, orange, and red, or whatever those colors you might want to, I mean, that's what I see. Those are the nonmetals. So the nonmetals live in the upper right-hand corner. We have to throw hydrogen in with the nonmetals. It's kind of cheating, but you have to throw hydrogen in with it. But then everything else is a metal. Now, again, to repeat what we stated on the previous slide, the metals become cations. The metals are electron givers and become positive. The nonmetals in the upper right-hand corner, plus H, are takers. The nonmetals become negatively charged, and the nonmetals become anions. So let's just look at probably the most ubiquitous, most familiar ionic compound of all. And again, I would offer that your mom and them are familiar with this ionic compound. I'm pretty sure your mom and them know the formula of this ionic compound. It is the ionic compound formed between metal sodium and non-metal chlorine. It turns out that's not what we call it, and we'll mention that on the next slide. But what happens is the metal becomes the electron giver. It gives up an electron. The non-metal becomes the electron taker, and it becomes an anion. Now, first of all, let me point out to you, there's a story behind why the sodium gives up one electron. There's a story behind why the chlorine wants one electron. We're not here to answer that story. If you want the answer to that story, I would advise you to take a higher level chemistry class. All we are going to operate under is the premise that metals are on the left and they're the givers, nonmetals are on the right and they're the takers. What I will say, though, is that there is a balance of loss and gain. This goes back to Ben Franklin. Remember what Ben Franklin said is that charge in the universe is conserved. We do not create or destroy charge. It's all here. We just redistribute it whenever we do an electrical process. So if the sodium atom is going to become a cation, it's losing an electron, remember, to become a cation. Keep that in mind. To make a sodium plus one, you don't add a proton, you remove an electron. Now, what we're claiming then is that this electron is not swept under the rug of the universe. This electron is given to the chlorine. So there is conservation of charge. For every sodium out there that wants to give up an electron, it finds a chlorine willing to accept an electron. So nothing is lost or gained in this, except the fact that I now have two ions. And now guess what happens? These ions are oppositely charged, and they are sticky towards one another. Opposite charges attract, and so the sodium is compelled to stick to the chlorine. So when I write the chemical formula of this, I do so indicating the one-to-one nature of the combination and exchange of electron from the sodium cation to the chlorine anion. So the chemical formula I would write is NaCl. And when you do this, you always list the positively charged thing first. You always list the negatively charged thing second. Now notice I didn't put the +1 and the -1 as a superscript when I did this. And this is chemistry convention. You just put the symbol for the giver first, the symbol for the taker second. Now, before we move on, what I would also mention is that, as I said, why sodium decides to lose one is a story for a different class. They don't all lose one. All metals do not lose one electron. all nonmetals do not gain one. There are various numbers of electrons preferred to be lost and gained depending on what elemental form you are dealing with. As a matter of fact, oxygen never gains one. Oxygen always gains two. Nitrogen never gains one. Nitrogen always gains three. Magnesium never gives one. Magnesium gives two. Calcium never gives one. Calcium gives two. So why does calcium give two where sodium only gives one? Again, I would prefer that we don't concern ourselves with that question. Again, I would say if you're interested in learning why, take a higher level chemistry. But I will give you this bit of information that the chemists have done with regard to how many you like to give or take. Your column is a collection of similar elements to you. So the periodic table is piled up always with the same elements lined up in each column. If you go down the first column, it's hydrogen, sodium, potassium, rubidium, and so forth. All of them like to be +1. The next column over is beryllium, magnesium, calcium, and on down. They all prefer to be +2. So the table piles them up in the arrangement of their favored way in which to give electrons. But that's the only thing I'm going to say about it. We're not going to get into the gore in detail as to why those elements prefer to give 2 compared to 1. Okay, so when we name our chemical formula, we're just going to put the thing that was positive first and the thing that was negative second. And when you name the compound by tradition, I think we have all recognized this. We first name the cation first, and we name the anion second. But by tradition, and I think you've heard this before, the last syllable of the anion is changed to IDE. Okay, so if the nonmetal is chlorine, when it's in the compound, it's chloride. If the ion is fluorine, if it's in the compound, it's fluoride. If the nonmetal is oxygen, if it's in a compound, it's oxide. If the nonmetal is nitrogen, when it's in a compound, it's a nitride. Now, some of them drop one syllable, some of them drop multiple syllables. Like, for instance, arsenic becomes arsenide, but phosphorus becomes phosphide. Now, which ones do multiple syllables, which ones do one? I can't really answer that. It's probably tradition, how many syllables you drop off or whatever. But definitely for the anion, you change the name. The cation, no. Cations always stay the same name. So for the metal, you just name the element that represents that metal. For the non-metal, you say the first syllable of the name and you change its ending to IDE. So of course, in this case, we have sodium chloride, and I'm sure everybody listening knew that already. So the chlorine becomes chloride. The nonmetal is changed to an IDE ending when you name the compound. Okay, now let's now discuss and describe why this is called a compound. When I shake sodium chloride onto my French fries, and we all know that we do that. When I put salt on anything, I'm using sodium chloride to represent salt. First of all, I want to point out to you, to chemists, oh, I don't have that slide here, sorry. Thought I had it here, I must have it later. To chemists, there's more than one salt. To consumers, salt is always sodium chloride. But to chemists, it is anything that forms an ionic compound is a salt. But so let's talk a little bit about the ionic lattice and what happens when I shake salt on my French fries. Now, first of all, you should realize we're in a conundrum. Because when I shake salt on my French fries, we obviously can see the salt. White chunks fall onto my French fries, and I can hold my French fry up, and I can see the individual white chunks. But of course, I think we all are very well aware that that does not mean that I'm seeing one sodium and one chloride. That's not what it is. As a matter of fact, in order to be able to see it, there has to be a multitude of sodiums and a multitude of chlorines. I would even offer to you that your human eye, the human eye can probably begin to discern a crystal of salt when there are 10 to the 20, 10 with 20 zeros of sodium connected to 10 to the 20 chlorides. That's probably the limit of our ability to see the salt with a naked eye. So what this cartoon is going to try to represent is the connection of sodium to chloride at the so-called nanoscopic level. And when I'm speaking of the nanoscopic level, I'm talking about I magically get some binoculars that enable me to see nanoscopically, and now I can see matter at the size of individual atoms. So here's what I would see. I have a sodium cation. It has given up an electron. That's how it became positive. It did not become positive by adding a proton. It became positive by shedding an electron. Now, where did the electron go that the sodium sheds? Well, it attaches to a chlorine, and that chlorine is now called a chloride. So notice the charge is transferred. The originally neutral chlorine no longer has a balance of electrons on it. It has an extra electron. Now, again, the motivation for why the sodium gives and the chlorine takes, we'll save for another class if you would like. But this is what happens. And now they go through this deal in the back alley and they try to run away from each other, but they're inherently pulled together. Opposite charges attract. So this is an ionic attraction of opposite charges sticking them together. Okay, now just before we move on here, let me mention that I am drawing these cartoons of the sodium and chloride as if they're the same size. That is no way, shape, or form true. These ions are not exactly the same radius of size. First of all, remember there's a cloud of electrons around the nucleus. So the outer edge of the circle is representing sort of like in the solar system, if you like, the motion of electrons around the nucleus of the sodium and the motion of the electrons around the nucleus of the chlorine. Okay, well, guess what? There's way more electrons around the chlorine than there are around the sodium. And so, especially when you take an electron away from the sodium, that's going to make the remaining electrons shrink in a little bit. When you add an extra electron on to the chlorine, that's going to make its space around it spread out a little bit. So these spheres that I'm representing should not be the same size. They should be different size to one another. But I was drawing this with my own artistry, so I just made them the same size. The next thing I want you to recognize is that this does not happen on a 1 sodium to 1 chloride basis. Usually when you scoop into a jar of the sodium, you're scooping out 10 to the 20 sodiums. When I scoop into the jar of chlorines, I'm scooping out 10 to the 20 chlorides. So guess what? This happens over and over and over again. And the ions are all attracted to one another. So they stick to each other in a straight line. Now, not only do they stick to each other two-dimensionally, or one-dimensionally, excuse me, they stick to each other two-dimensionally. Notice there's a lineup of the opposite charge touching an opposite charge. Now, this two-dimensional thing continues in both directions. Now, I also want you to envision, not only does this happen two-dimensionally, as I'm showing here, it happens three-dimensionally, which I can't show. What do I mean by three-dimensionally? There should be coming out of the screen, sodium and chlorine, sodium and chlorine. Going behind the screen, sodium, chlorine, sodium, chlorine. So it grows this way, and this way. And literally, when you shake the salt onto your French fries, you're shaking out little cubes, not little, when you stop to think about it individually, massive cubes of sodium chloride, sodium chloride, sodium chloride, sodium chloride. Again, I will offer, if you can see it, 10 to the 20 connected this way to 10 to the 20 chlorides, 10 to the 20 sodiums connected to 10 to the 20 chlorides, 10 to the 20 connected to 10 to the 20, just so you can see it. And if you could look very closely at it, it would be cubic in its spread. Now, a couple other things to say. The charges on these not only attract sodiums and chlorides, they attract other things. Most prominently, water from the air. Water is inundating the air, and water, turns out, is pretty polar, meaning water has a little negative and positive end as well. This is what makes it capable of dissolving salt. I put salt in water and we know it disappears. That's because the negative and positives of the salt hide among the negative and positive of the water. This even also works in air. When I put a cube of salt, I shake it out of my salt shaker onto my French fry. Water molecules in the air are flying around. They say, "Ooh, I like this positive and negative thing down here, and I'm going to start to stick to it." So not only would you see a cube of sodium chloride, if you could see nanoscopically, it'd be coated with water molecules all over it. The whole outer edge of it would be covered in water molecules. That's a guarantee. So at the nanoscopic level, this is probably quite an impressive arrangement that this ends up making. Now, what chemists have decided is that we will call this the ionic compound because the word compound means a repeat of the fragment. So when you shake out sodium chloride, you're shaking out a huge number of sodiums connected out to a huge number of chlorides, and that is a compound. And the empirical formula, according to a chemist, is the lowest ratio. So when I write the formula, I write the so-called empirical formula, which is just 1 Na to 1 Cl. When in practice, it's gazillions of Na connected to gazillions of Cl. Now, another thing I would like to point out before we move from this is the fact that I have kind of shown these sticking to each other, touching side, touching side, touching side. What happens when I put the next layer on top of it? Do they stack right on top of each other? Meaning, exactly on top of the sodium coming out towards me, should I put a chlorine? Then exactly on top of the chlorine, should I put a sodium, and so forth? That's possible, but another possibility is that the next layer falls in the little gap between the top layer. Now, what I mean by that is let's take a bunch of ping pong balls and I put a layer of ping pong balls down, then I pour another layer on top. The ping pong balls probably are not going to sit right on top of each other. They're going to fall into the little crack, the little space that's created between four of them. Notice between an NaCl and ClNa, there's a little gap. What I'm saying is probably the next row sits in that little gap all the way across. Just like if you poured a bunch of ping pong balls, they would sit in the gap between the next layer below or above them. That's probably what these would do if you could look nanoscopically. But that's another interesting story. Believe me, chemists have studied for a long time now just how these pack when they're making the solid. So that's a story, again, for a little deeper understanding of what this ultimately is doing. Okay, now let's suppose instead of making sodium chloride, as I'm doing, I shouldn't have backed this all up like this. Here I'm making sodium chloride. Let me just change, and I'm sorry, let me just change my metal and my non-metal to potassium and bromine. What if I change them to this form? Literally, very little changes. Potassium is a cousin of sodium. What do I mean by that? They're in the same column of the periodic table. Cousins in the periodic table, groups of elements do the same thing. So the metal potassium is in many ways exactly like the metal sodium, particularly in its reactivity. So it's also going to want to be a +1. The non-metal bromine is a cousin of chlorine. What I mean by that is it's in the same group, which relative to the periodic table means it's in the same column. So being a non-metal, it will be an electron gainer, but because it's in the same column as chlorine, it'll be a gainer of 1 electron. So notice again, they make a handsome couple. The potassiums each want to give an electron. The bromines each want to take an electron. There is conservation of charge when they get together. Now, to me, a chemist, I would call this potassium bromide because, of course, remember, you name the cation first, you name the anion second, but I also might refer to it as potassium bromide salt. Now, of course, your mom and them just think of sodium chloride as salt, but a chemist thinks of all metal, non-metal interactions that do the similar behavior of compounding of ions as do sodium and chlorine. We classify them all as salts. As a matter of fact, if I filled a salt shaker up with potassium bromide, you would probably have a hard time distinguishing that it was potassium bromide and not sodium chloride, maybe until it made you sick. So if you ingested enough of this, I'm sure it wouldn't be very good for your constitution, but I don't think at first you'd be able to tell much difference. It would taste salty. I guarantee you that. Now, I don't recommend that you sprinkle potassium bromide on French fries, but I would tell you without any uncertainty that it would taste salty, and when you shook it out of the salt shaker, the potassium bromide falling onto the French fries would look very similar to the sodium chloride falling on the French fries. Okay, now the empirical formula of this, you name the cation first, the anion second, would be KBr, and I would name it, as I said we did before, ending of the bromine changed to bromide. So now we have a hierarchy, a system as to how we can do this for a wide variety of metals combining with nonmetals. Now, the other thing to note is that this would be the empirical formula of KBr, 1 potassium cation connected to 1 bromine anion, But now this is going to do the same thing. It's going to concatenate to one another over and over and over again. I will make an ionic lattice of this that again will look extremely similar to salt. It'll have very much the same characteristics. So again, to a chemist, this is a salt. And again, remember, I'm showing a two-dimensional representation. It should be three-dimensional, meaning stick a potassium next to a bromine, potassium next to a bromine, coming out towards me and going behind the screen as well. Okay, now there are also large collections of polyatomic ions. Some of them familiar to you, some of them not. We're not going to get crazy with this concept, but most of these polyatomic ions have oxygen. Most of these polyatomic ions are negative, so they're the anions, and they always hang around together. So there are lots of non-metals combined together to make polyatomic ions. And they always have the same charge on them that I'm showing here. Now look, again, I'm showing you a whole bunch of different names. I'm showing you a whole bunch of different formulas. I'm showing you a whole bunch of different charges. I don't expect you to know these. Even if I did, you could look them up on this slide. If I did, I don't, but you could look them up. You can look them up on the web. Sulfate is always SO4. Sulfate is always -2. It doesn't care what metal it's combining with. So sulfate is an anion. It needs 2 electrons. Where does it get the 2 electrons? From a metal. A metal will give the sulfate the 2 electrons that it wants. So again, charge is conserved. I can have potassium sulfate, sodium sulfate, copper sulfate, iron sulfate. In every one of them, the sulfate needed 2 electrons. In every one of them, the sulfate gets the 2 electrons from the metal. Okay, same thing is true with nitrate. Nitrate is always NO3. Nitrate always needs 1 more electron to build itself. Where does it get it? Does it get it from thin air? Does it conjure it up with a spell? No. The nitrate needs an electron and it gets it from a cation. Doesn't matter what cation it's combining with. Whether it's gold, whether it's potassium, whether it's calcium, whether it's magnesium, whether it's strontium. All these metals give the nitrate the 1 electron it needs to build. So I can have compounds of magnesium nitrate, strontium nitrate, gold nitrate. All these things are possible. Okay, now I think I have another slide of these formulas. There's just the point you should take from this. There are gazillions of polyatomic ions, almost all of them negative, almost all of them have O, and they will have the same formula no matter what metal they combine with. But I was just showing you several examples that we can put into a compound. Now, when you use them, you just put them in the compound with their charges that they need and put the compound together. So if I have sodium nitrate, sodium's going to give up 1, nitrate's going to take 1. You just combine them together to make this compound. And what I'm showing on this slide is that they connect together in exactly the same way that you would do so for the things we already talked about. They connect together over and over again and make a compound. So there's a compound of sodium nitrate. Again, you could put it in a salt shaker. You could shake it on French fries, and it would taste salty, I'm going to guarantee, and you would hardly even know until you got sick that you weren't ingesting sodium chloride, probably. Okay, so some compounds use H as the cation, and I just wanted to point out to you, when they use H as the cation, we have a different name for them. we call them acids. So ionic compounds with H cations are always called acids based on what polyatomic ion or monatomic anion they're combining with. HCl, familiar to many people, is hydrochloric acid. You can buy it at in the pool supply area because people use it to clean their deck. You pour a little hydrochloric acid on the deck and it kind of melts any nasty oxidized cement off the top. You can rinse it away. So it's really good for cleaning cement. It's often called muriatic acid when you buy it in the store, but it's very commonly used as a cleaner of cement. Sulfuric acid is in car batteries. Phosphoric acid is in Coca-Cola. So if you taste small quantities of acid, they give kind of a bitter taste or kind of a tingly taste in your mouth. Citric acid is one that we often encounter when we eat fruits and vegetables. Another one that we commonly encounter is called acetic acid, which is vinegar. When you ingest vinegar, you're eating or imbibing another acid form that has H as a cation. Now, again, what do I expect us to know from this is that when you have a cation of H, instead of calling it an ionic compound, we more often call it an acid because of all acids seem to have the same kind of properties of dissolving and chewing up metals and chewing up cement and things of that sort that are very commonly used in a bunch of different applications in society. Okay, now I think what I'm going to do, I don't want to start talking about molecules. To a chemist, molecules are different than compounds. I think I'll save that discussion for Monday. So what I'm going to do is just stop our discussion at this particular point. I think certainly another thing I'm going to do is be putting out the remainder of the questions that we're going to be doing for our second test. I think I might, since the last one didn't go so good, I'm going to try my best to make the answers straightforward. Just look up the information on the slides, put the answers to the Moodle things in there. Because believe me, again, I don't want you to think I'm here to be your enemy. I don't want to be your enemy. I'm just going to try to put the information on the Moodle so that you can get things from the other sections on magnetism and a little bit about the flow of charge things that hopefully you can just look up and get your answers for from the Moodle stuff. So until next week, peace out. Oh, I'm supposed to turn this off. Stop that.